Right. Hello, everyone. So this is me with my colleague Efe and presenting our semester project, Platooning with V2X, for the class of Traffic Modeling Simulation and Control. So our objectives for this semester project are to realize a realistic topology imported from a real junction in Hungary. Here we've taken the one between M3 and E79 junction, and we developed a PD controller for maintaining a constant gap as a cooperative active cruise control. And for safety logic, we implemented a dynamic strategy for vehicles exiting the platoon to avoid any accidents. We analyzed the system's stability under varying channel noise levels at the end to see at which levels it remains stable even with packet loss. So this is a visualization of the junction that we created or we taken from Sumo Web Wizard. And so we generated the map on OSM Web Wizard, and we've taken it to Sumo for the road traffic physics and route generation. And then after it got ready from there, we've taken it to OMNeT++ using veins for simulating the network. And with Tracy, it connects the network commands with the vehicle mobility. So the data protocol on WSM is composed with a beacon message structure. And the content that is in this message is the sender's ID, meaning who is sending the message, the speed information, the lane information, which is composed of the road ID and lane index used for aligning, and the status flag, meaning that an exit flag would be equal to 0. 0 means staying in the platoon, and 1 means exiting, and also the position of XY coordinates. The cooperative adaptive cruise control mode is using the control mode 30, and that's because using the default mode of 1621 can create a misleading illusion of success. If a vehicle is avoiding a crash with a vehicle in front of it, it will maintain a constant gap, and that can make us feel like we are having a control over the platoon, where it's just the Sumo mode taking over. And so by using the mode 30, it removes any collision avoidance logic that is imposed by Sumo, and it forces the platoon to rely only on the custom cooperative adaptive cruise control PD controller for safety and gap maintenance. And so in this flowchart, we can see the life cycle of a single vehicle in the simulation, and we can see that from the start, it verifies if it is a node 0 or not. A yes would mean that it would get into leader mode by driving a fixed speed profile, and that it would keep broadcasting frequent beacons. If not, then it would check that if there is a beacon being broadcasted at a distance that is under 50 meters and over 1 meter. If yes, then it would take the join condition of a distance less than 50 meters, and the sender must not be exiting. The follower mode would compose of changing the color to green, read the leader's road ID and lane index, and then attempt to change lanes to match the leader. If there is no beacon under a distance of 50 meters and over 1 meter, then the vehicle would continue to drive normally and would not join in any sort of platoon. Going back to the follower mode, so in this, the vehicle would keep working in loops. So it would check the route. Is it an exit route? Because if yes, then the route ID would be set to exit platoon route, and the car would be set to a yellow color. It would set its flag to 1, meaning it's exiting the platoon. It would set the speed mode to 31, and it would set the lane change mode to 1621 and leave the platoon. If not, then it would lock on the same lane and keep checking that. On the other side, we have the cooperative adaptive cruise control, and it would check if the predecessor car is exiting. If no, then it would maintain a gap of 6 meters, which is a tight formation. And if yes, then it would set the effective desired gap to 30 meters, and this would also work in a loop.
So in the cooperative adaptive cruise control logic, we used a simple proportional derivative controller, but added a small caveat that is the dual stage control. So what we mean by this is that we also taken into account what the gap in between the vehicle and the predecessor have. So the gap error is a variable where we calculate the difference between the distance to the predecessor and effective desired gap. So with this, if the gap is too much, more than 15 meters, we tell the controller to speed up with regards to the gap error and catch up to the predecessor to close the gap. And at stage 2, which is the maintenance stage, if the distance is less than 15 meters, this means that we can give control to the PD controller and try to maintain the gap that we have, and we set in the key parameters. So we played around with key P and key D as variables, so which one would work better, and we've tried some more aggressive values, but we found out that this was the most stable and was able to keep the platoon in a long period under even noise, so we decided to go ahead with this. And as extra limits, so these are mostly for safety and to prevent exaggerated responses to the gaps. We set the maximum acceleration and deceleration, and to basically not overreact to the distance and have a crash, an accident, or actually decelerate more than it's supposed to be and cause a crash with the car behind them. The overspeed protection is also something around the same line as well. So the predecessor speed plus 8 meters per second is our maximum allowed speed. So if the controller tells us to go faster than this, we ignore it. We set the speed to the maximum of the predecessor plus 8 meters per second, because otherwise it could go too fast and cannot decelerate in time and crash into the car in front. So we have different lane logic. So for example, in an active platoon, the cars are forced into the same lane, and like Ibrahim told, it's in the VSM data protocol and which road they are in as well. And when the cars are merging, if they're not in the leader's lane yet, which otherwise, if this logic wasn't there, it would cause a crash because that lane wouldn't have that index. They use a mode 1620, which is the default sumo, to merge in safely. So we didn't implement the how to merge the cars because sumo already had it. And in the joining, in the complete joining session, we cared that the collision avoidance was there and the safety gap was also kept before the mode 30 takes over and our controller has all the control. So, and at this level, when the platoon was stable, the only thing left as a task that was asked from us was to test this platoon logic under different noise levels and to find at which level does it lose stability. We went another way and we tried to go from top to bottom and try to see at which point would it stop having accidents. And implementing the noise, we used this method that we created a random variable between 0 and 1. And if it was less than the noise percentage that we set, we just skipped on VSM function in the OMNeT code, which effectively is a package loss because we don't run the controller in that cycle. So in scenario A, where we just use the ideal channel, and this just gives us the result that the platoon is working, it's stable, there's minimal error. And in the scenario B, we started off with 60% package loss, which means 60% of the messages sent were lost. And at this level, the lost packages caused accidents because the vehicles were missing the required position information and velocity information of the predecessor. And this was causing accidents, which we'll be seeing in the video. And as scenario C, there was the 45% package loss. And at this level, there were still collisions and there were the effects of accordion. So they were acting like an accordion, so to speak, and was still not stable in order and also safe in this case. And finally, at scenario D, this is where we stopped because at 30% package loss, it was observed that the logic was able to keep up with the losses and it was not causing any, let's say, catastrophic failure. And at this point, we stopped testing any further because it was already stable. And one last important thing that we mentioned in the debugging of last presentation, the second presentation, we believe that during the conversion from OCM Web Wizard, some roads were having different troubles, let's say, and some cars were getting stuck randomly and they were not moving, even though we debugged them showing their state in which part they are in code, but we just couldn't find the reason. So finally, we added the solution that we added a variable that says, when was the last time this car drove? So it moved. So if it passed 3 seconds, we made the controller logic let go of this vehicle and hand it over to Sumo. And Sumo waits another 5 seconds to see if it's going to move, or if it's going to make any action. But if it doesn't, we use this time to teleport value. And this means that it was put into ghost mode and teleported a bit in front, a small distance, and this resumed all movement. Of course, this is some kind of a workaround. In a more realistic and more in-depth analysis, it would be better to go over the road simulation in NetEdit and make sure there's no trouble. So going into the video, Ibrahim will talk about the first parts.
So here we are looking at the zero noise level and zero packet loss as an overall view. And we are seeing that the platoon is forming in the beginning. There's the other node that got teleported, and we can see the different cars that are exiting. They're showing the status of exiting, and the other cars joining the platoon. They are also becoming a follower in the status. In the close-up view here, we will see the platoon starting, all the messages being sent and received by the platoon leader and the cars, and the gaps are not being held perfectly. In that case, they change from bigger to smaller, and we also can notice that the platoon leader starts at a slower speed for the formation of the platoon, and then it speeds up as we set in the staged up.
In the 60% noise, here we can see that the node 16 will teleport in front because at this level there was not enough control to contain stability. And at 45% package loss, we still observe, unfortunately, an unstable platoon where you can see the node 11 just jumped, and this is the natural way of Sumo handling crashes, that it just teleports it a bit in front. And at 30%, and finally, package loss, we can observe a stable platoon where they still have minor accordion effect movement, but still it is stable and it moves, and the exiting cars are exiting perfectly, and we cannot observe it, but the followers are joining as well. So thank you for watching, and if there are any questions, of course, we can answer them through every channel that you can contact us. Thank you.
Thank you.